One small change to Friday's quiz, and this is me, I wasn't here at this time last year, so just getting used to the timing of how long these lessons will take. 12.2, we're actually going to get through the whole lesson today. It's not one that necessarily needs to be split into 2 days. So you will get through part of 12.3 tomorrow before the quiz. So it's not changing the date of your quiz. Instead of moving the quiz up, I just added a little bit to what will be on it. So just a heads up on that. But for today, working with angles and angle measures, and I'm not quite sure from geometry how much of this, if any of it, will still be some review. But a couple of things you want to get out of today, being able to draw an angle in standard position, so understanding what that means. We will be working with converting degrees to radians and then radians to degrees, so we'll talk about what a radian is, and then we'll also be finding arc length and applying that to some different problems. So at the top here, we have an angle on the coordinate plane is in standard position if the vertex of the angle is at the origin, and one ray is on the positive x-axis, so that would be this ray here. So the ray that's on the x-axis is called the initial side of the angle, and then the ray that rotates about the center is called the terminal side. So this particular angle is rotated to here. This would be the terminal side of the angle. So these two rays are what create the angle. And then what I also want to make a note of on this diagram, so you're always starting, the positive x-axis is considered 0 degrees. If you go up a quarter of the way, you're at 90 degrees. Continue going another quarter, you're at 180. So 180 degrees makes a straight line. You may remember that from geometry. Go another quarter, you're at 270 degrees. All the way around a circle, how many degrees is that? 360. So 0 degrees and 360 degrees are actually in the same place. We'll get to that part later. They're considered coterminal angles. So what's in this key concept box here? If the measure of an angle is positive, the terminal side is rotated counterclockwise. So we start by going up and around counterclockwise. Versus if the measure of an angle is negative, the terminal side is rotated clockwise. So you would start by going down, and then you're going around clockwise that way. And then one other piece of information, the terminal side of an angle can make more than one complete rotation. So one complete rotation is 360. So for example, a complete rotation of 360 plus an additional rotation of 120 forms an angle that measures 360 plus 120 or 480 degrees. So that's what this angle would be to sketch an angle of 480 degrees. You would make one complete rotation and then go an additional 120 to draw your terminal side. So we're going to look at 3 examples. Draw the angle with the given measure in standard position. And if it helps you, you can always label 2, again, the positive x-axis, you're starting at 0 degrees. If you go up a quarter of the way, you're at 90 degrees. Go an additional quarter, you're at 180. An additional quarter, you're at 270. And then all the way around, you're at 360. So you're estimating a little bit of the placement of your terminal side of your angle if it's in between any of those measures. So the first example wants us to draw an angle that is 210 degrees. So I know I'm starting on the positive x-axis. I'm just going to sketch in my initial side. And I know 210 is between 180 and 270, so it would be about 30 degrees past 180. So the terminal side is going to end up being about here. And then you actually want to draw in the path your terminal side is taking. So I'm starting at 0 and going to the terminal side of 210, and then going around counterclockwise because it's a positive angle measure. So to draw an angle in standard position, that's it. Bless you. Questions on that? Okay. It's more just about figuring what direction you're going as well as the placement of your terminal side. So then, example 2, an angle of negative 45 degrees. So again, we're starting on the positive x-axis at 0. The angle is negative, meaning we're going to be going clockwise, so we'd be starting by going down. And then that means going clockwise, if I were to go a full quarter, this would be negative 90 degrees. So negative 45 is exactly halfway between 0 and negative 90. So my terminal side would be exactly halfway between them, and then I would draw the path that terminal side takes to get to the negative 45. Okay, the last example for this, example 3, 600 degrees. So again, starting at the 0. Now 600 is greater than 360. So this is going to be an angle that makes more than one complete rotation. So I know for sure I have to go around one time completely. So I have to go around 360 degrees. How many degrees do we still need to go to get to 600 degrees? 240. So let's see again. This is 180 over here. This is 270 down here. So 240 would be 60 degrees past 180. So terminal side would be about here. So I would keep going around all the way to that terminal side. Then if you want to make a note here, we went a full rotation of 360 plus we had to go an additional 240 degree rotation to get to the 600 degree angle. So any questions on drawing angles in standard position? Okay. So then we have, and I did mention this a little bit with the 0 and the 360, but 2 or more angles in standard position with the same terminal side are called coterminal angles. So for example, angles that measure 60 degrees, 420 degrees, and negative 300 degrees are all coterminal as shown in this figure here. So we see this terminal side. We can get to that terminal side by just going 60 degrees. We could go one complete rotation and another 60 and be at 420 degrees. We could also go clockwise around 300 degrees and be at negative 300. So all 3 of those angles have the same terminal side. They're all coterminal. To find coterminal angles, these can be found by adding or subtracting a multiple of 360 degrees. So, for example, with our 60 degree angle, if we added 360, that would give us the 420 degrees. And then if we subtracted 360, that would give us the negative 300. So that's how you can find them mathematically. And then obviously, too, these are not the only 2 angles that are coterminal with 60 degrees. You could continue adding 360 or subtracting 360 and have infinitely many angles that are coterminal. So in examples 4 and 5, you're just finding an angle with a positive measure and an angle with a negative measure that are coterminal with each angle. So you do need to make sure in your answers that one is positive, one is negative, because there are more than just 2 possible answers for these questions. So if we have the angle 210 degrees, to find a coterminal angle, I know I can add 360, and that would be 570. So that would be a positive angle that is coterminal with 210. I can also subtract 360 degrees from 210. And that would be negative 150 degrees. So that's a negative angle that is coterminal. Again, though, these are not the only two possible answers. I could continue adding 360 to 570 and subtracting 360 from 150 and get additional answers. So multiple answers there. Any questions on example 4? Okay. Are we good on that, or did you want me to explain example 5? All right, we'll move ahead. If you have questions, you'll have time to work, so just let me know. This next part then is introducing radians. I believe radian measures were introduced in geometry as well, I think. So this might be a review. But the top just defines a radian measure, so what a radian is. And I did mention yesterday that your calculators can be in degree mode or in radian mode, so depending on whether the angles that you're inputting into trig functions are measured in degrees or radians, you will get different answers depending on what mode you're in, so you want to make sure you're in the correct mode. So it says here angles can also be measured in units that are based on arc length. So a radian is based on arc length. 1 radian is the measure of an angle theta in standard position with a terminal side that intercepts an arc with the same length as the radius of the circle. So it's a bit wordy, but you can see from the picture here, theta is representing 1 radian. And where that terminal side intercepts the circle, that arc is equal to the length of the radius. And that then creates 1 radian. So that's how a radian is defined. So it's based on arc length. So therefore, the length around an entire circle would be the circumference. The circumference of a circle is 2 pi r, so 2 times pi times the radius. So 1 complete revolution around a circle is equal to 2 pi radians. So all the way around a circle is 360 degrees, but in radians, it's 2 pi radians. So therefore, 2 pi radians is equal to 360 degrees, and we can relate radians and degrees by the following equation. So we could also divide both 2 pi and 360 by 2 to see that pi radians is 180 degrees. So if you go all the way around a circle, you're going a length of 2 pi radians. If you only go halfway around, you're at pi radians. So pi and 180 degrees are the same. So these are the equations or the formulas you would use, the conversions I should say, to go between degrees and radians. So if you want to go from a degree measure to a radian measure, you would multiply the number of degrees by pi radians over 180 degrees, or just simply multiply by pi over 180. If you want to go the opposite direction, you have a radian measure and you want to convert it to a degree measure, you would multiply by the reciprocal of that conversion factor. So you're multiplying by 180 degrees over pi radians, or 180 over pi. And I'll show too in the examples why the conversions are the way they are. It's all about canceling out your units, just as if you were converting, say, between feet and inches, or even inches and centimeters. It's a conversion similar to that. So we'll get to examples of why we would need to convert between degrees and radians. But first, 6 and 7 are just practicing converting between the two. So you'll see directions that say rewrite the degree measure in radians and the radian measure in degrees. So the way to know if an angle is given to you in degrees or in radians, if it's given in degrees, you will see a degree symbol. If it's given in radians, the degree symbol will not be there. Most of the time, a radian measure includes pi, but not always. So the way to know if it's degrees or radians is just look for the degree symbol. So if we are starting, for example, 6 with 120 degrees, I want to convert this to radians. So I'm starting with 120 degrees. I'm just going to write that over 1. So I'm using this first conversion in the box above, going from degrees to radians. So I need to multiply by pi radians. And you can abbreviate radians too with RAD. But pi radians over 180 degrees. I'm including the units here to show you why the conversion is the way it is. So what happens when you multiply by this conversion factor, think cross-canceling. The units for the degrees cancel out, and therefore you're left with the units of radians. So that's why the conversion is the way it is. But then I can also cross-simplify the 120 and the 180. I could divide them both by 60. So the 120 would become a 2, the 180 a 3. And you do want to leave your angle measure in terms of pi. So don't type this in and get a decimal approximation. So multiplying across the numerators and denominators, you would have 2 pi over 3, and that's a radian measure. You don't have to include the units of radians if you just had 2 pi over 3. That's fine. But that would be converting degrees to radians. Questions on that? Okay, now we're going to do the reverse. This is a radian measure because we don't have a degree symbol. So we want to convert this to degrees, so we have to use the conversion of 180 degrees over pi, so just the reciprocal. So if we're starting with negative 3 pi over 8, we're going to multiply by 180 degrees over pi radians. Now I didn't write this, but because the negative 3 pi 8 is already measured in radians, here the radian measure cancels out and you're left with degrees as your unit. So that's why, again, the conversion is the way that it is. And then we can cross simplify here as well. So the pi's cancel out. And then we could also simplify the 8 and the 180 and divide them both by 4. So the 8 divided by 4 would be a 2. 180 divided by 4 is 45. And then if we multiply across, because that's as much cross-simplifying as we can do, we have negative 3 times 45. So that would be negative 135 over, in the denominator, we just have 2, and this is degrees. And you can then actually divide negative 135 by 2 and have a decimal as your measure. So 135 divided by 2 gives us negative 67.5 degrees. And you would want to make sure that you do have degrees in your answer. So the radian, RAD, you don't have to include that if you have a radian measure, but if you have a degree measure, you need to include the degree symbol to separate the two and know that that one is degrees. Any questions on converting? Okay, why you might need to do this. And I will say if you are going on to take trig pre-calc next year, you will work both with degrees and radians. More so as you move higher in math, and even as it's applied in higher level science courses as well, radian measures are typically used. So for example, I teach AP Calc. AP Calc does not use degree measures whatsoever, it's just radians. So radians are a little bit easier to use for different reasons, but just know that if you are taking trig pre-calc, you'll become very familiar with radians. But where these would be used, we have the central angle of a circle is the angle with a vertex at the center of the circle. If you know the measure of a central angle and the radius of the circle, you can find the length of the arc that's intercepted by the angle. And this is the formula that we use to find arc length. Might look familiar. I think it is covered in geometry. So for a circle with radius r and central angle theta in radians, so your central angle to use this formula has to be measured in radians. Meaning if you have a central angle given in degrees, it has to be converted to radians first. Then the arc length, which is notated with S, equals the product of r and theta. So this is your formula for arc length here. S equals r times theta. Arc length is radius times your central angle measured in radians. And then there's a diagram as well of what you're trying to find where everything is located. So in example 8, we have a circle, has a diameter of 9 centimeters. Find the arc length if the central angle is 60 degrees. And we know arc length, S is r times theta, radius times the central angle in radians. So first of all, if we know the diameter is 9 centimeters, what's the radius? Or how do you find the radius? Divide it by 2. So the radius would be 4.5 centimeters, half of the diameter. And then for theta, again, theta needs to be in radians. And right now, our central angle is given to us in degrees. So that has to be converted first. So if we have 60 degrees, I'll put that over 1. To convert this to radians, I multiply by pi over 180 degrees so that the degrees cancel each other out. And then I can cross simplify the 60 and 180, divide both by 60. So 60 becomes a 1, 180 divided by 60 is 3. And then multiplying across, we get pi over 3, or pi thirds. So pi thirds is our angle theta in radians. We now have everything we need to find our arc length. So arc length S is equal to the radius is 4.5 times the central angle in radians is pi thirds. And this you can approximate, so you don't have to leave arc length in exact form. If you want to approximate it to about 1 decimal place, that's fine. So I can multiply this by just calculating 4.5 times pi divided by 3. So it would be about 4.7 if I round it to the nearest tenth. And that would be measured in centimeters for this example. Any questions on example 8? Okay, so that one is very straightforward. Questions like number 9, where it might be applied. So we have the steering wheel on a monster truck has a radius of 11 inches. How far does a point on the steering wheel travel if the wheel makes 4/5 of a rotation? So if we're looking for how far a point on the steering wheel travels, we are still looking for arc length. If we picture this here, picture this as our steering wheel, and say we're starting where we would have 0 here. We're making 4/5 of a rotation. So 5/5 would be all the way around. So 4/5, picture the B here. And we are looking then for this length. How far that point would have traveled is what we're looking for. And we're given the information a little differently than we were for number 8. So here we are just given the radius. We don't have to find the radius. We know the radius is 11 inches. But we are not given the central angle that we need to find. Based on how this is worded, if the wheel makes 4/5 of a rotation, that means our central angle will be 4/5 of a full rotation, and a full rotation in radians is how much? What radian measure is that for a full rotation? 2 pi. Okay, so 4/5 of a rotation means 4/5 of 2 pi is going to be your angle theta. And I'm using 2 pi and not 360 because we want it in radians. So you're multiplying 4/5 times 2 pi. If it helps, you can put 2 pi over 1. So this would then be 8 pi fifths. That's the rotation we made. That's our angle theta. So then to find arc length, S, we're multiplying the radius times our central angle theta. So that would be 11 times 8 pi fifths. And again, we can approximate this using a calculator. So I can type in 11 times 8 pi divided by 5. So it's about 55.3 if we round it to the nearest tenth. And this would be measured in inches.